So these are the solutions to practice test 2 for Phys 1221. So in this first one, we've got a capacitor with C1 is equal to 4 microfarads. And it's connected across a 12-volt battery. And the question asks us, what charge is stored on each capacitor plate when C1 is connected across this battery? So we want to know what's this plus Q, and on this other plate we'll have minus Q. And so this is part A. So to work that out, we can use our capacitor equation that the capacitance is equal to the total charge over the voltage difference. Because this capacitor is the only thing in this circuit component with this 12-volt supply, the voltage across it is 12 volts. So we can rearrange this and get Q is equal to CV, and C we're given is 4 microfarads, so that's times 10 to the minus 6 farads, and then we times that by 12, and we end up with 4.8 times 10 to the minus 5 coulombs. So we've got a charge of plus 4.8 times 10 to the minus 5 coulombs on one of the plates and minus 4.8 times 10 to the minus 5 coulombs on the other plate. So one plate has plus 4.8 times 10 to the minus 5 coulombs, other plate has minus 4.8 times 10 to the minus 5 coulombs. Sorry about the messy writing. Part B then asks us what charge is stored on each plate when C1 and C2 are connected. But the question tells us that it is disconnected from the battery. So what we end up with is our charged capacitor here, C1, which is connected to our second capacitor, C2, here, like this. So we actually know the total charge. We know that on one side, if this was initially this positive side here, and this is this negative side, then on this side of this capacitor system, we've got plus 4.8 times 10 to the minus 5C. And on this other side, we've got minus 4.8 times 10 to the minus 5C. So we know that Q total, this is the total charge which we've got here, is equal to Q1 plus Q2. So this charge gets distributed between this plate and this plate, but there's nothing in this part of the circuit that can create or destroy charge. So the total charge remains the same. The other thing we know is that because these are connected in parallel like this, they must have the same voltage drop across each of them. So just rearranging our capacitor equation up here, we've got V is equal to Q over C. So we can write that as Q1 on C1 is equal to Q2 on C2, because both of these capacitors have the same voltage drop. So now we've got a couple of equations that we can solve simultaneously. So what we're trying to find now is the charge on this plate here. So we can rearrange that and say, well, Q1 is equal to C1 on C2 times Q2. And we can now substitute this into this equation here. So this gives us that the Q total is equal to C1 on C2 Q2 plus Q2, which is equal to Q2 outside of C1 on C2 plus 1. Okay, now Q total we know it's 4.8 times 10 to the minus 5 is equal to Q2. We know C1 was 4 microfarads, while C2 is 6 microfarads. So because that's a ratio, we can leave off the microfarads. So we've got 4 on 6, and then we've got plus 1. And so so then what we can do is say, well, Q2 is going to be equal to 4.8 times 10 to the minus 5 divided by the 4 on 6 plus 1. So solving this on the calculator, we get Q2 is equal to 2.9 times 10 to the minus 5 coulombs. And then we can find Q1 this way. So Q1 is equal to C1, which is 4 on 6, C1 on C2. So again, ratio, so I can leave off the units, times Q2, which is 2.9 times 10 to the minus 5. And so this is equal to 1.9 times 10 to the minus 5 coulombs. And so now we've worked out the charge on each of these capacitor plates. We've got plus 2.9 times 10 to the minus 5 on this one, minus 2.9 times 10 to the minus 5 on this one, plus 1.9 times 10 to the minus 5 on this one, and minus 1.9 times 10 to the 5 on that one. Okay, so now that we've answered it, let's have a look at how we would go about marking it. Now, for recognizing that we need to use this capacitor equation here, we would get 1 mark. We'd also get 1 point for solving it to find Q, and then 1 mark for this statement about one plate having the positive charge and one plate having the negative charge. For this second part, we would get 2 marks for recognizing that the Q total doesn't change and stating what its value is. So somehow recognizing that that value is equal to this. So that is worth 2 marks. We then get 2 marks for recognizing that the voltage is the same. So this equation here. And then we get 2 points for solving them simultaneously, so equating them this way. So we then get 2 marks for solving it for the first of these that we solved it for, and 1 mark for solving it for the second. So in total, this is out of 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 marks. Okay, so question 2. Okay, so in the first part of this question, we're asked to derive an expression for the magnetic field inside a solenoid. So let's sketch our solenoid like this. And to find out the magnetic field inside it, we're going to need to make use of Gauss's law. So to use Gauss's law, we need to choose a Gaussian surface. So let's take a rectangle like this, and we'll let it have a length L. And Gauss's law tells us that the integral of B dot ds is equal to mu naught I enclosed. So what we'll do is we'll consider what's going along each of these sides of the rectangle. Now, if we assume that this side is a very long way away, then we have no magnetic field at that point. So we can assume that along this side here, the integral of B ds is equal to 0. Now, with these two sides, they will also contribute 0 when we combine them together. One way to consider that is to consider the direction of the magnetic field. If we know it's this way along the solenoid, then ds and B are perpendicular to each other, so that's a 0 contribution. The other way to argue it is that because this one here is going down and this ds is going up, they're in opposite directions, so they will cancel out. Probably the first way to argue it is slightly preferable. So all we need to worry about is this side here. This is the only one which is going to contribute to this. So we've got B times this side, the integral of ds over this side is just the length of that side, so that's L, is equal to mu naught times I enclosed. So what we now need to do is work out, well, how much I is enclosed. So now what we need to work out is, well, how many turns of wire are inside here. So one way to do that is to take the linear density of the turns of wire, so that's N over L. This gives us the total number of turns per meter, and then times it by L. That will tell us how many turns are inside this box, but what we want to know is how much current, and each of these contributes a current I. So what we can say is, well, BL is equal to mu naught times N on L times little l I. Rearranging, well, the L's will cancel off, which tells us that the magnetic field inside is given by mu naught Ni on L. Oh, sorry, that's a capital L, the total length of the solenoid. Now in part 2, we're told that the current varies as a function of time. So we've got I is equal to I naught cos omega t. And we're asked to derive an expression for the induced EMF across the solenoid. So we know that the induced EMF is given by minus n d phi b dt, where phi b is the magnetic flux, so that's b dA. So for our solenoid here, the cross-sectional area, it's just a circle. So we know what the magnetic field is. It's constant inside our solenoid. This has got a constant B inside it. So we've got our B, which is mu naught Ni on L, times our area, which is pi r squared, because it's the area of a circle. So in order to work out the EMF, we have minus n times, we just need to worry which of these change with time. Everything's remaining constant apart from the current. So we can pull out all the constants. So mu naught n on L pi r squared, and then we've got di, and we'll put I naught cos omega t dt there. And so this is equal to minus n squared mu naught on L pi r squared times omega. Now, when we take the derivative of cos, we end up with minus sine. So that negative will cancel out and we'll end up with a sine omega t. So that there is our expression for the EMF. So let's look at how this is marked. There's 1 mark for realizing that we need to use Ampere's law, 2 marks for showing the Amperian loop, 1 mark for somehow recognizing that around this one, and this one, the contribution to Ampere's law is 0. We get 1 mark for showing that the integral of ds is L, so we're just considering this side here. We get 1 mark for calculating the enclosed current, and then 1 mark for substituting in. We don't get any marks for this final expression because that's on your formula sheet. So the first part's out of 7 marks. And then with the second part, we get 1 mark for Faraday's law here. We get 2 marks for calculating the magnetic flux. We get 2 marks for substituting in the magnetic flux, and then 1 point for our final expression. So this part here is out of 6. So the 6 and 7 gives us a total of 13 for this question.